Just get my slides running here. Okay. And thank you to the International Copper Association in Europe for inviting me today to come share some results. I've a study we concluded a few years ago on the energy efficiency opportunities for industrial and commercial motor systems within the United States. As Fernando mentioned, I'm Prakash Rao at Lawrence Berkeley National Laboratory. We'll get started. Just a very quick scan of what we'll cover today. We'll first start with an overview of the project on which I'll be reporting, the U.S. Motor System Market Assessment. We will proceed from there to discuss findings on the installed base of U.S. industrial and commercial motor systems, followed by some examples of energy efficiency opportunities within the industrial commercial motors installed industrial and commercial motor system base. As Fernando mentioned, just as a quick update, I'm at Lawrence Berkeley National Laboratory. There's an aerial shot you could see from there on the right, where one of, I believe, 17 national laboratories within the U.S. Department of Energy. Our focus, my focus at least, is on energy efficiency, particularly in the manufacturing sector. And we're located in Berkeley, California, so quite far away from some of our the European attendees today. Okay, I would be remiss to not start by mentioning the wonderful work of my project team on this project. So along with Paul Schaefer and myself, we led this effort. Yu-Ting Chen served as our principal statistical analyst. Alex Newkirk worked primarily on a supply chain component to evaluate the supply chain advanced motors and drives for this project. I won't be presenting on that today, as primarily because the information hasn't been updated since we first published the report, and things could have changed. So, and Pat Fitzgerald, who's no longer at LBNL, but and Nick Karki, who is at LBNL, assisted with a lot of the analysis. I want to make sure that and be cognizant of terminology differences. Some of the folks that helped get the study off the ground kind of have trained me to understand that some of these terms are different. So just to make sure we're all speaking the same language and we all kind of understand each other, you're going to hear me use the word industrial a lot. I just want to ensure when I say industrial, I'm referring to the manufacturing sector. Just traditional manufacturing, steel making, chemical production, semiconductor manufacturing, automobiles, planes, etc. But we also included municipal wastewater treatment facilities, municipal meaning those that serve residential and commercial communities. So nothing private on site. I'll use the term commercial. These are essentially non-residential buildings. These are your schools, your offices, your hospitals, your shopping centers, those sort of facilities. I'll unfortunately use the word horsepower. All our results are in horsepower, not kW, not kilowatts. But if you can keep in mind, 1 horsepower is about 3/4 of a kilowatt. Premium efficiency is the NEMA designated efficiency class for motors, equivalent to about IE3, I believe, in Europe. And I'll use the term variable frequency drive, or I'll abbreviate it to VFD. This is motor speed control that's electronic. And finally, load factor. When I use that term in this presentation, I'll be referring to the percent of full load of the end use demand. So if you can imagine, I need so much CFM and PSI of compressed air. It's the fractional percentage that I'm actually using of the total rated capacity. Okay, so with that, we'll get started. So I wanted to start really quickly by placing us in context a little bit, right? So electricity consumption in the United States is very central towards reducing energy costs for our businesses, both the commercial businesses as well as manufacturing businesses. I don't need to explain in too much detail why this is important, but it certainly reduces production costs in the manufacturing sector and makes that sector more productive, from an economically at least. On the left is a chart of the all energy flows in the United States. So you can see if you start all the way on the left-hand side, it starts with where we get our energy, from solar down through petroleum. As you follow this Sankey flow chart, you will notice it will track you through where that energy is going. So we're about 93 quads of energy. I believe one quad is about a petajoule. I think that's correct. And we're about 32 units of electricity generation out of that 93.6. And then you'll see the residential, commercial, industrial, and transportation there. Now, electricity generation, which we'll be talking about electrically driven motor systems, and they're 34%. So electricity generation is 34% of all U.S. energy consumption. And 30% of this is going to industrial and commercial facilities. So what that means is motor systems, as we'll show, are a substantial portion of the electricity consumption in the United States, as motors consume a lot of the electricity that's going to the industrial and commercial space. And we'll identify how much that is in the ensuing slides. And perhaps most importantly, if electricity is free, we probably wouldn't care too much about it, but it's not. It can be quite expensive, to the tune of in the United States in 2023, industrial and commercial facilities paid close to $500 billion in electricity fees. This is from the U.S. Department of Energy's Energy Information Agency. And industrial and commercial facilities bear about 53% of these costs. So that's about $260 billion for electricity in the United States for industrial and commercial facilities. And again, going back to what we'll show, that's a lot of that is motor systems are the reason for that electricity consumption. Okay, one of the challenges that we had, faced in the late 90s was the information we had on U.S. motor systems up until the current study that we'll present on was getting outdated. It was at the time of the study initiation, it was about 20 years old. So kind of the first of its kind in the late 90s, the U.S. Department of Energy, working with motor manufacturers, trade associations, and the like, conducted and published a study in 1998, a comprehensive assessment of industrial motors and motor-driven systems based on actual data collection from 1997. Now, this is on industrial, and about a year later, they did a similar study, though I don't believe it was less comprehensive, however, it was for commercial motors. So just focusing for a bit on the industrial study in 1998, you'll see the cover right there on the right. Maybe some of you have seen it. It was a very monumental study, and that it was, again, first of its kind for us. And you can point to some of the energy consumption, energy efficiency opportunities that were identified through the survey, and then assistance to kind of get manufacturers to implement some of these ideas, motor manufacturers to kind of work towards making more efficient equipment. You could see there was a noticeable impact in sort of how we used our motor systems, including the market uptake for technologies to address any losses. However, it was 1998. It was when the data, or 97, I guess, when the data was collected. In the late 2010s, it was clear that the information was different. That the current situation in the United States was different than it was in the late 90s. We had offshoring of industry for various reasons. We had costs of motors and variable frequency drives, or particularly variable frequency drives, dropping. We had the electric utilities creating all these, using the data from the 1998 report, creating all these incentive programs to make it cheaper to upgrade your motor systems, or at least defray some of the costs. So there was reason to believe that the market for the installed base of motors was not the same as it was in 1997. So it was clear a new study was needed. And that's when the Department of Energy initiated the motor system market assessment. Lawrence Berkeley National Laboratory led the assessment, along with and worked with some contractors to get the work done at Cascade Energy and D&V GL. And we had the support and guidance of, and I'll list them later, but of wonderful organizations like ESA and NEMA and Hydraulic Institute and AMCA over here in the United States to help guide the technical foundation of the study and get it done. So a new study was performed to more fully understand energy opportunities for energy efficiency improvement within the U.S. industrial motor system base. One huge difference between in the latest study, in the 97 or 98 study, was that it wasn't just going to look at industrial, we were going to do commercial as well. So it was almost a 2x increase in work scope. So the new assessment looked at both industrial and commercial motor systems. And essentially our goal was to, very simply put, from the market assessment, understand what's installed, how it operates, and not just the things like load factor and operating hours, but also understand the environment in which it operates, the maintenance procedures, how it's procured, how the systems are designed, as we believe that there might be a lot of efficiency opportunities there as well. That was the market assessment. I'll also present results on the identifying and enumerating the enumerating the energy efficiency opportunities, and that was using the data. That was another goal. We hope to inform strategies for reducing electricity costs associated with motor systems, help understand technologists, what new technologies are needed for motor-driven systems, help utilities or state, local, federal, whatever governments promote energy savings programs within, and particularly energy cost reductions within motor systems, and also develop more technical assistance material, software, written literature, tools, whatever it might be, to help end users understand how to lower their electricity costs associated with motor systems. And I note there that the study was completed in 2023. That was the last. There were 4 components of our study, or products, let's say. We have 3 reports and an online platform that hosted the reports, but also hosts the rolled up data, so folks can go in there and understand motor systems themselves within the United States, and how much are for pumps and for what purpose, for example, for pumping systems. And the 3 reports, volume 1 outline what's installed and the operating characteristics and maintenance procurement design practices. Volume 2 was essentially a review of the supply of what we know about the supply chain for advanced motors and drives, particularly those rare earth materials that are involved in them. And then volume 3, which came out in 2023, was the energy efficiency savings opportunity for motor, industrial, and commercial motor systems. So I'll be presenting on those results today. Okay, well, I've been saying motor systems a lot. What do I mean by motor systems? So a motor system is any polyphase motor. What was in our scope for our assessment was any polyphase motor, 1 horsepower, again, so at 0.74 kilowatts or greater. Large direct current motors, I've written in there over 50 horsepower, but frankly, we didn't see as many as we thought. So in fact, if we did see a DC motor, regardless of size, as long as it's above 1 horsepower, we collected information on it. We looked at all motor systems, so anything with a motor, that's again, polyphase over 1 horsepower. So pumping systems, fan systems, compressed air systems, refrigeration, material handling and processing, and then general purpose motors were all within scope. 2 notes here. I mentioned that the commercial sector was an expansion from the 1997 study. A couple other expansions. The 90 study did not look at HVAC, so ventilation motors, as it was believed that wasn't a significant contributor to industrial motor consumption, and we'll show that's actually not true. And I believe they didn't also look at materials processing motors, which is also substantial. We found to be substantial. And now the system, you can see a little cartoon there, is the drive and the control, so if there is one, a VFD or whatever it might be, the electric motor itself, any gearing or belts that are involved in the transmission of that mechanical power, to the driven equipment, which is of course included, so the pump, the compressor, whatever it might be, and then through the distribution system. So it could be the compressed air lines, the air ducts. We evaluated those as well. So that's the full system. So basically, it starts with the electricity coming into the facility and ends with whatever that medium is, if it's water or compressed air, whatever it is, at the point of end use. Okay, so I don't think I made just to make it explicitly clear that our methodology for gathering information was actually boots on the ground assessments. So we sent engineering teams out into the field to manufacturing industrial facilities. They spent a day, sometimes two, collecting a full inventory of the motor systems at the facility, answering a whole list of questions that we had designed. I like to tell people, one of my learnings after completing this study is where I went into it thinking it'd be a highly, technical from an energy engineering standpoint study. And while it was, I would probably say the part that I didn't appreciate as much and perhaps was even more difficult was the statistical side of this. And that might be because I'm not a statistician, but we want to ensure, so there's 185,000 manufacturing and wastewater facilities in the United States. I actually think it's 185,000 manufacturing facilities with additionally there's there you see 14,000 wastewater facilities in the United States. So closer to 100,000 facilities that we had to gather information on. Of course, we're not going to 200,000 facilities. We had about a generous, frankly, ability to go about 250. So we had to judiciously allocate these 250 samples that we could do of actual physical assessments in such a way that we can then statistically roll that information up and understand what's the full picture in the United States and in this case for industry. So we picked two strata, statistical strata, so to speak. We used industry type, and we used a very standard definition that we use here in the United States, the North American Industrial Classification System, which breaks manufacturing down into, I think it's 21 industries. You'll see them both on the right-hand side in that table and then below the text box, but also you can see them on the x-axis of the graph. What I'm mentioning, this disaggregation. And then within each sector, we also want to recognize that there's small, there's medium, and there's large facilities. And so we want to, and we believe the installed motor systems and how they use them could be different between a very large facility and a very small facility. So there you'll see our allocation of samples based on the population of facilities. The population of facilities is on the right, allocation of samples is on the left, and broken down by small, medium, large. Small, medium, and large, we broke down using employee count. Okay, so then on the commercial side, we basically did the same thing, except the commercial side, the numbers are a little bit different. As you might imagine, in the United States, at the time of the study, we had 5.5 million commercial buildings. There's a little bit more heterogeneity in commercial facilities than compared to industrial facilities. So we had about half the number of samples, 123 assessments. And again, physical sending people out to facilities assessments. And we also, again, broke down by small, medium, large. This time, we used floor space as opposed to employees. And there you can see the breakdown of samples, office buildings, educational facilities, and warehouses and storage received the most samples. Okay, so on the assessments, what did we do? So again, it was 1 or 2 days. It was a team of 2 to 3 engineers. Mostly 1-day assessments. There's only a few 2 days for things like large steel mills. We would collect information about the facility itself for a statistical roll to place in the right context. And then we could collect identifying information for the facility, such as the sector, its address, but also its annual electricity and energy consumption, number of employees, square footage, excuse me. And then we've continued on to collect an inventory of the installed base of motor systems. So any motor over 1 horsepower, we generally try to collect its nameplate information. We try to understand its operating hours, typical load factor, if there is any adjustable speed drive, such as VFD on it, transmission type driven equipment served, understanding the motor history, its repair history when it was installed. Where we couldn't determine this by just looking and seeing and gathering sort of written information, documented information, we also relied on our guide through the facility who oftentimes knew and oftentimes didn't too. For any system that we believe was a larger consumer of energy, so that we wanted to get a little bit more fidelity on, we define this as any motor system over 20 horsepower and operating over 2,000 hours. So, a larger energy consumer. We collected some additional information to determine improvement opportunities. What is the type of driven equipment and what is it rated at? And more information on the load factor, what is part of the system, maintenance and procurement and considerations and history for these. We tried to collect more information on that with these checklists. And then finally, to understand a little bit better about the environment which these motors operated, we collected motor system maintenance and management practices of the facility, and energy management practices. How do they identify energy efficiency measures? How often do they install them? Where do they get the information from? We did evaluated the distribution systems to understand if they're leaky or what sort of repair they're in, and additional questions. Okay, well, that's a little bit about what we did. Hopefully that was all clear. So now we'll move on into the results of the installed base. So installed motor systems in the United States, we found to account for about 29% of the overall electric grid load in the United States. So if you kind of do the numbers really roughly, I think earlier I'd said about 30-something% of all energy is for electricity generation. So 29% of that 30% is about 10% of all energy in the United States goes for motors. Someone should check me on that. I just did that in my head. But but a large amount of energy goes for industrial and commercial motor systems. To the tune of 116 billion with the B dollars per year in electricity costs for the across, the industrial and commercial sectors. So that's within the industrial sector, 69% of electricity consumption is from motors. So if you're talking electricity in industry, it's likely a motor. 13% of industry's overall energy consumption. This seems kind of low, but manufacturing is primarily thermal processes, so a lot of it's fossil fuels, but still 13%. And also remember the cost angle is what we're interested in here. 18% of emissions from scope 2 emissions from electricity generation, but $47 billion per year in electricity costs. Within the commercial sector, motors represented 43% of its electricity consumption, so less than industry by share, but there's more lighting in commercial facilities, so it's a little bit more mixed. But 26% of its overall energy consumption, and $69 billion per year in electricity costs. The chart on the left shows where we're at, a little bit more breakdown. So commercial and industrial about the same, about 532,000 for commercial and 547,000 for industrial gigawatt hours per year in electricity consumption, netting to over about 1 million gigawatt hours. So I think that's about 1 terawatt hour or 1,000 terawatt hours of electricity consumption. So that's gross consumption across industrial and commercial sector. If we look at what is a motor being, what type of motor system is using it, we have refrigeration, fans, pumps, material processing, compressed air, and materials handling. Netted across the two, industrial and commercial refrigeration. So this is like your chillers, your air conditioning systems, consumed the biggest share of electricity at 319,000 gigawatt hours to a tune of $38 million, so $38 billion in cost. And you could see fans was close behind in terms of the motor systems that are consuming the most energy. And then as we get into further breakdowns, I think you'll understand why. So for example, right here, energy consumption by driven equipment, again, sort of taking that same information from the last slide, but looking at this specific for industry and commercial, you'll see in industry, the largest motor-driven system was materials processing. If you recall, that wasn't something that was examined as closely in the 90 study, but here we found that it was actually quite a substantial contributor to motor system energy consumption. So what are we talking about materials processing? These are things like grinders, hydraulic actuators, extrusion machines, those sort of things. But this is followed closely by fans and blowers and pumps, so moving air and water around. Within the commercial sector, it's quite a different snapshot of the end use motor systems. Within the commercial systems, it's primarily refrigeration compressors and fans and blowers. So that's your HVAC, right? And your air conditioning systems. So when you think about, the previous result where we said that most energy consumption is refrigeration and fans and compressors, you could see commercials dominated by it, and industry has quite a lot of fans. And refrigeration is no tiny share either. This is a little bit of an ugly chart. I apologize for that, but we're trying to play with some visualizations when you have so much data. It can be kind of fun. So we have on the left-hand rail, you'll see the energy consumptions for industry by the same end-use equipment, the compressors, fans, blowers, material handling, et cetera. And on the right-hand side, we want to get one more step deeper and understand, well, what are you actually using a motor for? That compressed air that you're spending so much money and electricity cost to compress and send to your plant, what is it actually going to? So that's on the right-hand side. We have the energy for the motor systems going to compressed air plants, conveying, air handling, exhausting, gas compression, material shaping. Here you'll see some unsurprising sort of results. Fans and blowers, is going to air handling, other, and then a little bit going to process heating, process cooling, things like that. Materials processing is being used across air handling, extrusion, gas compression, hydraulic systems, material shaping, space cooling even, and the pumping systems are going for quite a variety of reasons. And on the right hand, you'll see the total energy consumption. Now, these slides will be made available just so folks know, but also if you want to play with the information yourself, there's motors.lbl.gov. That'll be a link at the end. You can gather all this information and cut it out however you want, or cut it up however you want. Within the commercial space, same sort of picture, visualization, but different picture. You have your energy, motor-driven systems, fans and refrigeration compressors are the largest. And you can see it's far less sort of end uses for the motor systems. There's air handling, refrigeration, space cooling. So it's a little bit of a simpler picture, but doesn't really make the challenges. Still a lot of opportunity. So that's looking at the motor system energy consumption by end use equipment. But if we do it a little bit differently and we look at it by those sectors that we discussed earlier, in industry, you'll see that the largest consumers of motor system consumption is our chemical sector. So this is making anything from chlorine to, I don't know, dishwashing soap. Mostly on the chlorine, the ammonias, and those BTXs and things like that are the largest consumers of electricity in the motor system consumption in the chemical sector, followed by primary metals. Primary metals is iron and steel, aluminum manufacturing, and then food, which is food, of course, but it's a smaller facilities, but disaggregated across the United States, netting to quite a bit of energy and particularly motors. Within the commercial space, the types of facilities that are using the most motor system consumption were offices, educational facilities, and then warehousing, lodging, so hotels. Okay, so getting a little bit into the system, how are the systems used? As I mentioned, we examined operating hours, or we queried operating hours. In industrial systems, we found that on average that these motor systems are running about 3,200 hours per year. This varies slightly by horsepower range, as you can see in the chart, though not marvelously until you get to about 1,000 horsepower. We saw less 1,000 horsepower and greater motors, so you'll see those quartile ranges are a little bit larger. So there's less samples in there, and that might be leading to some of those conclusions. In the commercial sector, the majority of the energy consumption is in the smaller horsepower range. I don't have that chart here for industrial commercial, but the vast majority of the energy consumption is under 50 horsepower. So you kind of see that here, but also it's about 3,000 hours operationally. Looking at load factors across all motor sizes, large motors tend to be more underloaded than small motors. And why this matters, from the left is a chart that I grabbed from the literature. Many of you kind of understand this already, so I won't go into detail, but as we kind of drop on load percent of full load, we hit a knee almost in the energy efficiency of the motor, and it's a precipitous drop for that knee once you hit it. So it's important to keep motors loaded. And frankly, for the smaller motors, the load factors weren't horrible. They're quite higher than we expected, but it does trail off, meaning drop, as we get to larger motors. Commercial systems is a little bit flatter. Again, most of the motor consumption was under 50 horsepower. But we do see, so for example, in the 50, 100 horsepower range, quite, 50% load factors. Now, load factor alone isn't what we want to understand. We want to understand load variability. So is it underloaded, and is it, is that constant or variably loaded? So we examined that as well. On the industrial side, 45% of the motors were constant load. So we asked, is this system constant or variable loaded? And based on what they said, we'd then ask, okay, is it typically below 40% load, between 40 and 75% load, or greater than 75% load? Just a quick caveat here. We initially did start by actually doing logging and trying to understand motor load factor that way. It clearly was going to just run through our budget in very quickly, installing the CTs and things like that to understand, or the load monitoring instruments to understand what the load factor was. Required a lot of safety and time. And if we have hundreds of motors at the plant, we couldn't do it for all one of them, and then it'll just be a spot measurement. So we did an initial 10 assessments to try to understand, to get our feet wet and understand what's a good way to do this. And unfortunately, that was one of the things that we felt we're going to be spending a lot of time to get a little bit of data that might not even be that representative if it's just a spot check. So we reverted to asking. We also asked, so then we'd also, so we asked if it's constant or variably loaded, and then some load factor bins. And we also report unknown. If we did not know, we are reporting that. So you'll see our sums, 45 and 38%, don't add up to 100. Similarly, on the commercial side, about 5% of the motor systems they didn't really know. But 64% were variably loaded, and 31% constantly loaded in the commercial space. Okay, so that's there's plenty of more information on the installed inventory. We could probably spend hours on it, but just to give you some high-level overview, that's I'll leave it there and encourage you guys to look at the reports and the website, and we'll move on into the energy opportunities, or energy savings, energy cost reduction opportunities. So there's several opportunities we examined. So within the drive and the controller, any losses across the drive, at the motor itself, inefficient motors, if it's the rewind status, if it's very low load factor, transmission, the type of transmission, if there's slippage or friction that's leading to losses. At the driven equipment, improper maintenance, improper set points, improper sequencing of multiple compressed air systems, for example, could lead to losses. Within the distribution, poor design or poor maintenance, poor condition is a common or things that could lead to losses. But then across the whole system, is the system just inefficiently meeting demand? Is the system being used for things it really shouldn't be used for? These are some of the things we want to examine. And today I'll just highlight results from the 3 bolded ones. losses associated with inefficient motors, losses associated with poor condition of distribution systems, and losses associated with inefficiently meeting demand. Okay, and the other losses, it won't be on our motors.lbl.gov site. It's going to be in the volume 3 report, so you can check that out, which you can get from the motors.lbl.gov site, but the data is not for the losses isn't published there. So upgrading the motors, so the inefficient motors, starting with how old are these motors? We want to understand how old motors are, and it was a very interesting result, somewhat sobering, and that within the commercial space, we found that about 50% of motor counts, we couldn't determine the age. And in industrial space, it was even higher. The reason being the nameplate, for example, would first try to look at the nameplate. If it's wiped out, washed out, painted over, whatever, we can't read it. So then we ask the facility contact. If the facility contact doesn't know, there's no written documentation, then it's an unknown motor age. So with that, the age of the motors we could discern all typically were skewed towards kind of younger motors. However, we think that's an artifact of, well, the older motors, probably those are the ones that we couldn't collect the age on because it was installed before the guy got there that we were talking to, or, it's old, so the nameplates, undergone some wear and tear. But we wanted to understand the age of the motor to understand when it might have been installed, what efficiency regulations were there at the time, and then kind of impute what the efficiency might have been. So we, with the data we did have, we moved forward anyways. And what I've listed here is you can see the efficiency of the installed base at various horsepower sizes for the commercial and industry sectors. And then you'll see what the premium efficiency or the IE3 performance level is. So if we replace that motor ASAP and updated it with a premium efficiency motor, that percent difference in efficiency is what you might expect. So upgrading motors to premium efficiency, we found about a 3% energy 3% energy savings across sort of motor system energy consumption between the two sectors, about $3.5 billion in savings. And now, as you recall, one of our stakeholders here is our utilities, or folks who are in a position to kind of motivate these changes. So one thing we could try to do, or not we, but someone could try to do, is provide financial incentives. So we want to understand what would the incentives do? How big would they need to be? If you were going to purchase a motor and you went to utility and said, "Hey, I'm going to purchase a motor. It's energy efficiency. It's the right thing to do. Can you give me do you have a rebate program? How much money would move the needle, so to speak?" With the note that, at 2016, the U.S. Department of Energy required that most new motors between 1 and 500 horsepower meet the premium efficiency standard, but a lot of motors are old. So there's a lot of motors. The standard might be there, but standard's only effective when folks go to replace the motor. So how can we spur early replacement? So on the left and the right, you'll see I'll try to walk through this. At current premium efficiency motor costs, of the 15, just stay with industrial for a second, of the 15,571 gigawatt hours of savings that we have identified, about 2,600 that would be cost effective immediately, right away. Cost effective we determined by a simple payback of under 2 years. But if you start to add incentives such that 25% of the costs are defrayed, so the motor is 75% of current costs, you'll see you'll be able to move more motor systems into the cost-effective category. So you could see those sum there. So if we go to 50%, so if someone were to pay for half the motor cost, you're going to realize about 5,000 gigawatt hours of savings. That's under a 2-year payback. So that's a great payback, great financial sort of argument there to do it. The commercial side, the incentives would need to be a little bit larger, as you could see in the chart. And in order for it to be cost effective and for early replacement. Okay, so improving condition of distribution systems. This is something that was an exciting result in an odd way, and that there's so many losses in distribution systems, and there's a significant opportunity for improvement. So this is after the motor, after the drive, after the motor, after the gears, after the pump. That's now you're moving whatever thing you energized with the motor through the facilities. What's the condition of those ducting? So we did inspections and we gave them grades. So best practice, good, fair, poor. You can see right there what that means. A lot, and then there are the results. A lot of the systems were good to fair, and hardly any were in this best practiced zone, which is perhaps a high bar, but nonetheless not really being achieved. So going from the current distribution level to the best practice level, compressed air systems would have realized 8%. Well, it was 8% loss going within compressed air distribution systems is just in the piping, moving the compressed air around, 5% losses in the water pumping, the distribution systems, 5% losses in air ducts that could be attacked with better sort of design and maintenance of distribution systems. And then current load matching techniques. So we did talk about sort of the load factors. Okay, so how are they matching loads? This is a little bit small, but you can grab this information. You can grab yourself at the motor.lbl.gov site. As you'll see, in both on the left industrial and on the right commercial facilities, there's not a lot of load control. When we go to the VFDs and the one that folks are most interested in, and industry is about 16% uptake of VFDs. Some sectors are pretty great at it. We mentioned chemicals as being the largest energy motor system consumer, and they got 35% of their connected horsepower at their facilities is on a VFD, so that's wonderful. Commercial side, much lower uptake, 4%. Hospitals, which is the HCI there, and then educational facilities had some, noticeable penetration, but by and large, not a lot of VFDs in the commercial sector. And again, so we want to understand, okay, what's the opportunity for load control, but improved load control, so or sizing. So we, if a motor is constantly loaded but under 75% load factor, we examined it, if it's the right candidate for, if it's a candidate for right sizing, and if a motor system is variably loaded at all, it was a candidate for VFDs. Within that, using that paradigm for VFDs alone, not the right sizing, so the variable loads, we found about a 10% energy system, motor system energy, electricity consumption savings opportunity, to the tune of about $12 billion, $13 billion almost per year. And again, we looked at the cost effectiveness of these. I do want to kind of speed up so I can leave some time for Q&A, but so I won't go as in detail here, but a little bit different picture in that a large percentage of the VFD opportunity was already cost effective underneath the 2-year payback period. So it was clear to us that, the actual efficiency of the motor can be improved, but if you're going to do one thing, the load factor and adding VFDs appears to be the one that's going to be the most economically you should do it. All right, and then finally here, advanced motor systems or motor drives. We want to understand the market potential for things like permanent magnet motors, switch reluctance motors, synchronous reluctance motors, permanent magnet synchronous reluctance motors, and copper rotor motors. You all are much greater experts on me than on each of these technologies, so I won't go into this. In fact, I probably learned about these technologies from some of the people on this webinar. But on the right, you'll see the efficiency classes, levels for these motors across load factors. All the time, more efficient, the premium efficiency motors, and a little bit smoother with that knee efficiency drop that we mentioned. However, they do require a VFD, though switch reluctance motors are inherently variable speed capable. So we did want to do a fair comparison as best we could. So rather than just saying what's the opportunity for putting permanent magnet motors in industry and compared to the baseline, we want to really understand more if you have a system that requires load control or is inefficient. What's the savings if we upgraded that system to a premium efficiency system with the VFD, and then what is this? And what's the savings if we move to a permanent magnet motor or switch reluctance or et cetera motor system? And you'll see the results there. while certainly the permanent magnet motor, I think permanent magnet motors is a good one to focus on, because there we have motors in the 1 to 500 horsepower range. There's greater coverage. I think previously, as I showed, switch reluctance and synchronous reluctance motors, we didn't find on the market that many larger motors available. So we actually only evaluated those technologies for a smaller subset of the installed base, um, owing to the fact that we didn't know if it was commercially available for everyone. But permanent magnet motors seem to be for under 500 horsepower. But you'll see a slight improvement in energy savings. So the premium efficiency motors at the VFDs are quite wonderful at grabbing the energy savings. But there are additional benefits of these advanced motor technologies. They have greater power density, they're lighter weight, they're inherently line start with the VFDs, right? They support grid reliability with the load factor, and the way they charge up. Challenges are some of them require these rare earth materials, which can be hard to source. They're expensive. As I mentioned, they're not available in all size ranges. I have to fit them into the existing frame, and some of them can be loud, which is a real problem, I think, for switch reluctance motors. Okay, so in summary, industrial and commercial motor systems are about 9% of all energy related emissions, but more importantly, 29% of all electric grid consumption. They have the potential to reduce for the strategies we examined. Those are reviewed today, plus the others in the report. 17% of motor system energy consumption, 18% of costs. If you want to access the 3 reports, again, motors.lbl.gov. And I want to thank our folks at Department of Energy. This was at the Advanced Manufacturing Office. It's gone through a couple of different name changes. Now it'd be the Industrial Technology Office, but at the time it was Advanced Manufacturing Office. Supported this project. DNV did their statistical support. Cadmus, I think I said Cascade earlier, excuse me, it was Cadmus, did the field assessments. We also relied on U.S. Department of Energy's industrial assessment centers to grab some of the data for us. And we had numerous internal, external reviewers, both of the results, and then equally importantly, the kickoff to help us orient us. So folks from the National Electrical Manufacturers Association, ESA, Air Movement and Control Association, Hydraulic Institute, American Council for Energy Efficiency, Efficient Economy, and others. I want to thank them for helping us get this done. And I'll leave it there. My email is there, prout@lbl.gov. Again, motors.lbl.gov is where you can grab the information. And I will stop share and field questions.